So today you're able to access the test review sheets, and then I have two other documents there. Two other documents there. You got the test review under today's, and then there's also the summary sheets, kind of highlighting the important steps for that we need to be able to apply. And then I also have this direction for taking and submitting tests on Friday. So let me walk through this, see if you guys have any questions. I'm going to schedule the test to post as an assignment in our class Teams page. In fact, there is an assignment right there now, and then that assignment is kind of a practice or dry run for the just having you guys submit the assignment to see if you can write on it, see if you can apply the process, just so that by Friday we'll feel comfortable with what we're expected to do. But when you see the assignment on Friday, you'll see it as Unit 1 limits test. You're going to see it. It'll post 12 minutes before the start of the class to allow for lag time in the system posting. Okay. But as soon as you access it, you're free to start working on it. However, I gave the 10-12 minutes beforehand so that any setup that you need to do with it, you have time to do it, whether it's printing out, getting it ready so that you can actually take it on the physical piece of paper, or moving it into OneNote so that you can begin the process of taking the test. Okay. You must join the Teams call and stay in the Teams meeting with your camera on until you've submitted your test. Okay, so you're just going to have the camera on and have it facing you so that I can see your face and see your hand working on the test. You must submit your test as a Word document, and the reason why I need it as a Word document is because it will allow me to write directly on the test when I've graded, and when I finish grading it, I'll be able to submit it back to you or return it back to you, and I won't have to print it out and write on it and then scan it back in. It'll make my process a lot easier if you're able to submit it as a Word document. Now, if you were to, okay, let me just continue reading through here. So not a PDF, picture, or JPEG, or any other format, but I want to talk about how we can work around that. So therefore, ideally, writing directly into a document on your device is the easiest option. Maybe you go through OneNote. However, you may print out, right, then work on paper, then scan and take a PDF photo, and then insert it into a Word document. Sometimes that could be doing copy and paste. That could be using the snipping tool to move it into a Word document. And then make sure what you're submitting is legible. Practice how you're going to do this so that you can do it quickly and efficiently. And then the submission deadline is going to be 12 minutes after the end of the class period. So when the bell rings at the end of the class, you still have 10-12 minutes to finish up, to take a photo of it if you need to get it. If you get into PDF file, that's fine. And then once the PDF file, then you're going to find a way to move it into a Word document. So you will be able to finish this within 45 minutes if you understand the material. And so there's going to be a total of 9 questions, 9 problems. If you miss the submission deadline, you will not be able to submit via Teams, and then you have to email it to me immediately. If you have any technical issue, such as accessing it or getting into Teams, you can send me a remind message, or you can just go ahead and email me your question. Or you can email me your attachment of your Word document, or if you can't do it, then do a PDF file. So as your the assignment that is there right now for the practice run is just 2 problems. You can either choose to do it or not do it. Just you can write on it just so I can see that you're able to do it. And then there's 2 problems. So if you want to use this as a practice practice exercise, you can do that. But you're going to do 2 pages. It's going to be 2 problems on 2 separate pages. And if you can do that today or tomorrow, that would be great. And then you're going to find a way to do however way you want to do it. Either take it online, take it digitally, or take it on the physical after you print it out. But either way, practice getting it into a Word document and then submitting it to me. So I just want visual proof that you're comfortable and that you have a process down for Friday. When you go to your assignment, and this is going to be true on the test and this practice assignment, is that I'll have 2 files for you. There's a Word document version of it, and there's also a PDF version of it. Maybe the Word document will be easier for you to move into or to submit it back as a Word doc, and then the PDF file may be more will be maybe easier if you want to print it out. But I'll give 2 options, and then 2 of the same tests in different versions, and you can access whichever one you feel is easier for your process. Okay, are there any questions that you have right now? You know, we're kind of working through this as the first time, so I haven't gone through this either, so you know, we're kind of just learning as we go in terms of you know, maybe what issues, maybe I'm not able to identify what potential issues could occur, but you know, I'm hoping that if we all attempt this today and tomorrow, if there's any issues that come up, we can sort those out and still have time before Friday. So ideally, if you try this today, then any issues that you run into, we can discuss tomorrow. And if we want to practice another submission, we can do that for Thursday. And then by Friday, we should be comfortable. Okay, any questions at this time? So I will send out a text reminder this afternoon to just remind you to go to your assignment tab, look for the assignment, and then start working through that process of can you, whichever method you want to use, can you go ahead and write on the test, write on the practice test, submit it into a Word document, and I just want just visual confirmation that you're good and ready for Friday. I want us to finish the 1.4b notes. Well, we've done the notes. It's just there are some additional problems that that'll be good as test review that we didn't get to yet. So on the back of the 1.4b, we have 61 and 66. So we're going to spend time working through these problems, and this will be good for our test review as well. Let me first start off by reviewing continuity conditions. So if we want to prove the function is continuous at a point, we go through these conditions. The continuity condition is not going to prove continuity for the entire function, but we're only focusing at a specific point. So the first condition is, does the point exist? So let me just draw a diagram to help give us a visual. Let's say the point exists. Okay. Does the limit exist? That means, is the graph on either side of C going to be moving towards the same y value? Okay. If it is, right? If we can pick points on both sides and have it move towards the y value, and they're both pointing towards the same y value, we know limit exists. So here the point exists, the limit exists, and now the third question is, does the limit exist where the point exists? And here, this would fail, right? Because there's an obvious discontinuity. That hole is not getting filled in by that point. So if the third condition fails, we have something called removable discontinuity. If the limit fails, right, if the graph looks something like this, where if we pick points on either side and they're not leading us towards the same y value, then number 2 fails. So if number 2 fails, okay, we have a non-removable discontinuity. Okay, so I just wanted to review these conditions before we jumped into these problems. So let me read the instructions here. It says, making a function continuous. In these exercises, find the constant a such that the function is continuous on the entire real number line. But really, we're just going to find continuity at a point. There's an additional complexity to this in the sense that we don't know what a value is. We're going to have to find that a value. But let me set up, I want to talk about this particular type of piecewise function and how to visualize and how to expect what could happen with this type of setup. So this is telling us that we have different functions defined on either side of 1. Now, you don't have to draw a graph every time, but I just want to start off just by giving some visual connection with something that looks a little abstract. So ax minus 4 is some linear graph, right? It's not set in stone because we don't know what that a value is, but it's some linear graph that's to the left of 1. So maybe something like this. And then the 3x squared is a parabola that just happens to live on the right side of 1. So right now, these graphs, it may or may not connect, and we're trying to find an a value so that they will connect nicely. And let me just label these expressions for now. Okay, so we're going to step through the conditions and we're going to solve for a, but we don't have to do anything other than following our script. If we just follow the continuity conditions, everything will just play out where we know what's going to happen with a. So if we have our structure in place, we don't have to do anything different to solve for a. As long as we fall within the line of our conditions, it'll become obvious what has to happen to solve for a. Okay. So as I go through this problem, I'd like for you guys to answer. Not trying to put you guys on the spot, but if you can answer, try to answer, because it'll help me know. It'll help me gauge whether I'm moving too fast or whether whether you guys are following along. Okay. So if you know the answer, try to share it so that I can gauge where we are as a class. Because if no one answers, then okay, maybe I need to take a step back. Maybe I need to recap a few things, or maybe I've gone too fast. Okay. So all we're going to do is we're going to just step through our conditions. Okay. So the first condition is, does the point exist? Okay. So what do you think? What's our C value for this problem? What's the center of attention for this piecewise that we're looking at?
1.
Yeah. Right. You're never going to have to guess what the C value is. It'll always be given to you. Okay. Now, f of 1. Now, we have to figure out what f of 1 is, so we have to still decide which one to plug it into. So do we plug 1 into the ax minus 4, or do we plug 1 into the 3x squared?
3x squared.
3x squared.
And why is that? What's telling us to do that?
The sign where it's less than or equal to, or greater than or equal. Yeah, less than.
That little sign, right? That little equal sign tells us 1 is defined for 3x squared, but not for the ax minus 4. It'll get close to 1, but this is always to the left of 1. Okay, so that little notation there tells us 1 is defined for the first piecewise. Okay, so plug 1 in for x. Okay, so first condition. Let's continue on. Second condition, does the limit exist? So that means I need to pick points on both sides of my target, find a way to move towards my target, and see if they are arriving at the same y value. So now the question is, can we rely on one limit statement to do that? Or do we need two one-sided limit to help us through this process? What do you guys think?
Well, the one-sided is kind of built in almost to the equations because of the greater than and less than symbols. So you would assign numbers to either one based on which side of one they're on.
Okay. Okay. So you're saying that we do need one-sided limit.
No, it would be inherent to it, correct?
That's true. Okay. I mean, you're right. Everything is built in within the function, but can just one limit statement handle the approach from both sides?
No.
Okay, we do need two. Okay. And the reason that we need two is because we have distinct separate functions that define the behavior on either side of one. Okay. So that's what I want us to take away, is that when you see greater than and less than, this is an indication that when you get to your limit statement, you're going to need one-sided limit because you have two separate graphs and we need to evaluate them differently because they're defined differently. Okay. All right, so we're going to find the limit, but we're going to go through this process to confirm whether the true limit exists. So we want to approach 1 from the left side of 1. So right now, that's just a notation that we're starting at a point on the left side of 1 and we're moving towards 1, but it's obviously sitting on this ax minus 4. We also want to find the limit coming from the other side. And if we're coming from the other side, we're obviously working with the parabola, right? So that must be the 3x squared. All right, how do we evaluate these algebraically? Let's start with this one. How would you evaluate this algebraically? What's the first thing that we always do for any algebraic limit if we're approaching a real number?
We plug it in.
Okay, just the whole number, right? Okay, just the whole number. I know we see the one-side limit. Maybe you're thinking, wait, what if I do 0.9 or 0.99 or 0.95? Can I not do that? Well, we talked about how we only do decimals if we can confirm that there's a vertical asymptote. But we always want to plug in first to get the idea, getting a feel for what's happening at that point. Remember, we only use one-side limit algebraically. We only do something with decimals if we've come to the conclusion that there's a vertical asymptote and we need to subcategorize a vertical asymptote because it's either positive or negative infinity. So we never want to play with decimals to begin with, right? All right, so we just want to plug in that whole number because if it's approaching, if it exists, then there's no need to do anything. The one-side limit is going to be in agreement with the real limit or with the limit as x approaches 1. So we plug 1 in for for x. We get a times 1 minus 4, which is a minus 4. Okay, we'll leave that alone. We'll come back to it. On the other side, we want to figure out where's this graph approaching. So we plug 1 in for x. 3 times 1 squared is 3. Okay, we have our one-sided limits. We have something for our one-side limits. But remember, our goal is to try to make this function continuous. We want all of our conditions to pass. So what would you do with these one-side limits? What do we need to do with them?
Would you set them equal to each other?
Right. We're not doing anything. We're not coming up with anything, right? We're just following the script. In order for our limit to exist, the same condition has to pass. In order for a limit to exist, our one-side limits must be in agreement. So a minus the one side, as we approach from the left and from the right side of 1, these must be equal. And these must be equal, we can set their results equal to each other. And if we set the results equal to each other, we have a natural equation that allows us to solve for a. So add 4 to both sides, a equals 7. Okay, we have our answer here. So if we can let a be equal to 7, all of a sudden, we're able to adjust this linear graph so that it rises to the point where it's going to connect nicely with the curve on the other side with the parabola. Okay. So we have our answer, but I just want to convince us that it does pass all 3 conditions. So first condition, f of 1 equals 3. Second condition, once the 7 gets plugged in for a, 7 minus 4 is 3, 3 equals 3. We know the full limit must be equal to 3 because both sides are in agreement. And then the third condition is where we just look at the results of the first 2, and these are also in agreement. All 3 conditions pass. We've created a scenario where we can guarantee continuity at x equals 1 because we're able to solve for a. But you're not creating this equation out of the blue, right? It just naturally came up by just following our conditions. Any questions there?
Mr. Yang,
Yes.
so it says for number 2, a is equal to 7, but then right below it, you said f of x is equal to 3. I'm just really confused right now.
Got it. Okay. So what happens when I plug A back into my expression?
Wait, say it again.
What happens when I plug A back into my expression?
It's 7 minus 4. Oh,
Which
makes
is
sense. We're good.
3, right? So A is just a part of the. It's a portion of the limit, but it's not the full one-sided limit. Once we plug in, we confirm that we're getting a 3.
So it goes from ax minus 4 to just a minus 4. Why is that?
Good, right? Because we always plug in our x value for our whole number. So I didn't quite show that step. So technically what's happening is we plug in the a, it's a 1 in for x. So we get a times 1 minus 4, which is just a minus 4.
Okay, thank you. Sorry, I just zoned out for a bit. My bad.
That's fine. I'm glad. Yeah, I'm glad you mentioned that. Maybe some other students were wondering about that too. Good. Any other questions with 61? Okay, let's look at 66. The reason why I picked out 61 and 66 is because I want to talk about the restrictions. These are both piecewise functions, but the way that these are restricted gives us kind of insight as to how the graph looks, or what the graph looks like, and how the limit condition, how the conditions are going to play out, well, because of the setup. So this x squared minus a squared over x minus a. When you see this x doesn't equal to a, let me further expand on what that's saying. This is saying that this expression, right, this expression that we see is going to define the graph to the left of A and to the right of A. So both sides of A is going to be nicely compacted into this expression. Okay. Now, the only place that this is not defined at is at A. So there's a potential hole that may or may not get filled in. And that hole may or may not get filled in by the second piecewise, but this piecewise is not a connected part of graph. This piecewise is just a point. So here's the big picture. The big picture is when you see greater than and less than, you're basically wondering whether your two branches are going to connect at this specific point. Okay. When you see x doesn't equal to a and x equals a, that's telling you, that's showing you that there is a hole in the graph. And the question is that hole going to get filled in by this point? So because of the restrictions, we kind of have an idea as to what the potential issue could be. So with this one, the potential issue is going to be condition number 2. There's a potential possibility for the limit to not exist. This, however, the issue is not with limit. The issue is with does the hole get filled in by the order pair? Okay. All right, so I just want to kind of give you like a general visual so that when you look at the conditions, you kind of have an idea how to move forward with this type of problem. All right, but we're going to step through continuity conditions and convince ourselves what we can do to make it so that this will be a continuous function. So we have some flexibility, right? We can solve for a, but everything will just show up nicely within our condition here. All right, so what's our C value here?
A.
A, yeah. It looks strange, right? It's like, oh wait, that's not a real number, but you know, it's unknown for now, but we're going to eventually get to it. We just kind of take what they give us and we'll see how far it goes. So where's f of a defined at? What's f of a equal to?
8.
8.
Right? Because it's defined at a, right? It's not defined at a, so we don't use this one. We use the bottom one because that's what the restriction tells us. Okay, this is as far as we can go. Second condition, does the limit exist? So now my question here is, can we rely on just one limit statement, or do we need two one-side limit statements? What do you guys think?
Two.
Okay, we could use two, but can we get away with just one?
Yeah, because eight is just a point on the graph,
Okay.
and we don't need to. Yeah.
Okay, so you see this x is equal to a? This is telling us that everything to the left greater than a is with this expression. Less than a is also within this expression. They're not writing it out in so many words, but it's like saying x is greater than a and x is less than a is all the same function. But rather than writing out everything, they're just writing it as x doesn't equal to a. So when you see this notation, you got to just think in terms of less than a is with this, greater than a is with this. So we could use one-side limit, but then we're kind of duplicating our efforts because it's the same function on either side. But this one's different, right? This one is distinctly different functions on either side of 1. But this one is for less than a and for greater than a. It's just that it's everything but a. So if we're approaching the graph from the left and from the right side, these branches, both branches are defined by this expression. And that little notation tells us that. So x approaching a. Algebraic limit. How do you move forward from here?
Wouldn't you put an A for X?
Yep, plug in a for x, right? Okay. I get 0 over 0, so what does that tell us?
There's a hole.
There's a hole. There's an answer at the end of this process. We just have to do a little bit of cleanup, right? Eliminate the hole, reevaluate. Difference of squares. Just like what we expected, right? When you see 0 over 0, you're expecting something that matches that we can remove. What's next?
Substitute.
Yep, substitution, a in for x, a plus a is 2a. So we still don't know what the a value is, but at least we have some expression to work with. Okay, third condition. How would you set up your third condition?
You would set them equal to each other.
Right. We set the result of the second condition equal to the result of the first condition. So that means 8 must be equal to 2a. And the equation just naturally shows itself, and we can solve for a, right? We don't have to do any additional effort to figure out what a is. If we just follow the script, the equation that we need will just naturally show up. So now we can solve for a, right? A must be equal to 4. So if a is equal to 4, then we know this is 8, and this is 8, and this is 8. Then everything is going to be equal to 8. Everything is going to play out nicely. Our graph is going to be guaranteed to have a hole filled in by that point. Okay. I want us to practice with this type of a scenario again. So if we can turn to the warm-up problem. So spend a few minutes. This is not going to be one. This is set in stone. Okay, so we're not solving for anything. This function is set in stone. We just want to know, is there a discontinuity? And if there is, can we categorize what discontinuity we're working with? Okay. So try this problem. Give you guys a minute. And it's going to resemble the steps that we did for the problem that we just finished. Okay, so try that for a moment. Okay, let's see how you guys did here. Our C value is right at 2. So, and we know that we're dealing, if we want to find the order pair, it's with the second piecewise. So this x plus 7 is normally a linear graph, but we're cutting everything off except at a point. So this ends up just to tell us where that point is. The rest of the linear graph is completely cut off. So all we know is that order pair is at 7. Limit as x approaches 2, we only use the first piecewise. We don't use left is this and right is this, because to the left of 2 is the x squared minus 4 over x minus 2. To the right of 2, it's also the x squared minus 4 over x minus 2. We could use one-sided limit, but then we're just finding the one-sided limit for the same function. So might as well just rely on one limit statement. Again, this is just a point. So this is not a connected part of graph that we can use for our one-sided limits. So everything is, the connected parts of graph is all self-contained within this expression. So we set up our limit statement. We plug in 2 in for x, we get 0 over 0. We factor, eliminate, reevaluate, we get 4. So this tells us that there is a hole at 2, 4. And that hole may or may not get filled in, but then by the time we reach the third condition, we see that the hole is obviously not getting filled in because the point is in a different location. The order pair is at 2, 7. The hole is at 2, 4. These are not the same value. We have a removable discontinuity at x equals 2. So when you see this setup, it may be continuous, but if it's going to fail, it's going to fail the third condition. Okay. If you see this sort of a setup, okay, it may be continuous, but if it fails, it's going to fail the second condition. All right. So seeing the way that our problem is set up kind of gives us a hint as to what could happen if there's a discontinuity. Which condition is going to be the one that's going to be giving this problem, or this that could be the result of this problem, just based off of how the conditions are set up. Yes, question?
For 61, you said what condition would be affected? Or which condition would it work?
Right. So if you have a greater than and less than, you know that if it's going to fail continuity, it's going to fail because the second condition is not going to pass. Because the branches may be disconnected, and the branches are disconnected, it's going to be because of it'll fail the second condition.
All right, thanks.
But if I have a hole in the graph, and that hole may or may not be filled in by a point, then when you see this setup, it's either going to pass all 3 conditions, or it's going to end up failing the third condition. So it kind of gives you an idea as to what may happen, what type of discontinuity may happen, just by the way that these restrictions are set up. Okay, we're going to spend tomorrow going over this limits review, and I encourage you guys to print this out as well. So on the test, you'll be allowed to use this concept sheet. Spells out the steps for evaluating limits, has the steps for continuity conditions, and then also has IVT steps. Okay. All right. So have a great day, guys. See you tomorrow.
Thank you, Mr. Yang.
Thank you, Mr. Yang. Have a nice day.
See you guys. Bye.
Bye. Thank you.
Thank you. Bye, Grady.
Mr. Yang,
Yes.
do you have any textbook problems that you'd recommend, or do you think that's like just unnecessary?
Yes, I do. So what you can do is, here, let me show you.
Like something to focus on.
Oh, okay, like something to focus on.
General, actually.
Well, I would say if you can focus on the